record it. So we learned several kinds of motion, how to describe several kinds of motion. Linear motion, and then circular motion, and rotational motion, right? So now the motion that repeats goes back and forth, okay? Oscillatory motion, just like the motion of a pendulum. And it turns out that every atoms, I mean the matters, they are made up of atoms or molecules, okay? And they are always oscillating back and forth, just like pendulum does. So that's why it becomes very important that we learn how to deal with oscillating object, okay? And that's what we're going to be doing here. And it turns out the oscillation also produces wave. So if we know how the oscillating particle works, you know, how the motion of the, how do we describe the motion of the oscillating object, then we can relate that to the wave generated by the oscillating object. So for example, let's say I can generate sound wave by just tapping on my table here, okay? So what's happening? By tapping that, I'm making the atoms of this wooden table vibrate. And that vibration is producing the sound wave. In a light bulb, the electrons are kind of oscillating, vibrating. And that oscillation is producing a light wave. When electrons are jumping up and on and off because of the electric energy they receive, and when they pass through the filament, what happens? They lose some energy. So that oscillation is giving off some energy, and that energy comes out as a light wave, heat wave, okay? So these waves generated because of the oscillation. So that's what we're going to be talking about in this chapter. So here is a short video where these balls, they are just oscillating back and forth. And how quickly they are oscillating, going back and forth, depends on their slope, the curvature of that track here, right? How it's built. So looks like yellow is moving, you know, oscillating fastest, and so on. So that we call the time it takes to go all the way and back to the same place, that's the period of oscillation. So just like this different track, you know, the curvature, different curvature gives the different time period of oscillation. Similarly, different length of the pendulum gives you different period of oscillation. So we're gonna write down the equation for that today, folks. So for the oscillation, what are the things we need? So usually object wants to stay in equilibrium position. And if we disturb that object from the oscillating, you know, equilibrium position, then what happens? So this is equilibrium position. If we let it settle down, what's going to happen? It's going to go back and forth, just like we saw in that track. And then it's going to just settle down here. That's the equilibrium position. We talked about equilibrium and stability, right? Where we talked about the eddy stand and so on, right? So here it is being, let's say, displaced from its equilibrium position. Then what happens there? There's going to be a net force acting because of the normal force and the weight. So there are two forces acting. Yeah, there is a little bit friction as well, and that's what makes it roll. So let's forget about that friction. So if we add mg and n, what happens? To add that, I'm bringing tail of that mg to the tip of n. And then what happens? Now the sum I can draw by just starting from tail of the first vector, which is n, to the tip of the last vector, which is mg. I moved over there, right? So that's the net force, sum of n and mg. So net force is acting towards the equilibrium position. So because of that, it rolls downhill there. So that's the force that's making it roll downhill, okay? So now it rolls back and forth like that, right? And let's say when it goes to the other side, what happens? Net force again is acting towards the equilibrium position. So that's why it always want to come back to the equilibrium position, okay? So if it is already sitting on the equilibrium position and if we don't displace it, it's not going to oscillate. It's going to just stay there. So we need some displacement there. We need disturbing force a little bit, okay? Once we give that, then what happens is it starts oscillating back and forth. And now how long it's going to oscillate is going to depend on how much damping force is there or the friction is there. If too much friction, it's not going to oscillate longer, okay? So I think if you want that to keep going, then you want minimum friction possible, right? So anyway, oh, there is this question. So go ahead and answer, and you have a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. Oops, my bad. I need to delete that. And now it all messed up. So I think that's the response. A stable equilibrium. So if there is no stable equilibrium, it's going to just run away, not going to come back. So they're not going to be oscillation, right? So little or no friction. So if there is too much friction, then what's going to happen? It's not going to oscillate for relatively long time. So we are looking for relatively long time. So yeah, we don't want that one either. Large friction either. So that means 2 seems to be correct as well. And a disturbance. If there is no disturbance, then it's not going to start. So it looks like all of them, just like most of you identified it correctly. Okay. So what's the difference here? So ball, and the ball was rolling on that ball shape. And what's happening here? Oh, why that pendulum is not swinging here? Yep. So just like a ball rolls on the ball, similarly, the pendulum, see, is following the similar path. So there must be a restoring force for the pendulum as well. And for the ball, it came from what? Normal force. And remember, for the ball, there was no string attached, right? So that's what it was for the ball. without a string. So now for the pendulum, what happens? Pendulum with the string, what we have? Tension. And remember, it's not rolling on the ball, it's just swinging on the air, right? So that means there is mg. So it's the net force between T and mg. That gives this oscillation. So same idea here, see? And if a mass is attached to a spring, what happens? If it is in equilibrium, then it's not going to oscillate. But if we put some disturbance, pull it a little bit down and let it go, it's going to oscillate back and forth. And that's what's happening, right? Or it could be oscillating horizontal as well, okay? It's easier to demonstrate vertical oscillation, but it is easier to mathematically work with the horizontal oscillation. But they are equivalent as long as we are talking about oscillation about the equilibrium position. Remember, if it is already vertical, then what happens is its equilibrium position going to be slightly down than the length of the string because weight pulls it down already. Now you pull further from the equilibrium position and let it go, then it oscillates about that equilibrium position. The position when it wasn't oscillating, but mass was attached and it was sitting at that point. And remember, because of the mass, it's already stretched. So the equilibrium position is not same at the on stretched length of the string. It's not. But when it is horizontal, what happens is weight is not pulling the string. So because of that, what happens? Equilibrium position going to be exactly at the length of the string. Okay. So only that's the difference. And once we analyze the motion about the equilibrium position, what happens? The idea is same, physics is same, okay? So again, when they are oscillating, we can talk in terms of period of oscillation. So for the pendulum, it goes there and comes back. That's one oscillation, okay? For the pendulum, if it starts from here, that's one oscillation. That's the time for one oscillation, okay? And for this, what's happening? It's coming down, going up, and then coming back, let's say at equilibrium position. So that's what one complete oscillation means. Now frequency means how many times it's oscillating every second is the frequency, which is reciprocal of the period, okay? So this period is similar to a period in a circular motion. It's the same idea, okay? And later we'll see the circular motion and the oscillation, they are somehow related too. We can relate those kind of motion, okay? And for the oscillatory motion, we use angular frequency. We call that angular frequency. So for the rotational motion, we use omega, and we call that rotational speed or angular speed. So that's what we said for the rotational motion, okay? When object is rotating, let's say this object, when object is rotating, is spinning, right? That's what we said. Here, mathematics works out exactly same, but it has slightly different name. We call that angular frequency, okay? And angular frequency and linear frequency, they are related by just 2 pi f, okay? 2 pi. And since frequency is 1 over period, you can write like this as well. And this equation we use for the circular motion as well, okay? So equation wise, it turns out to be same. So now let's learn how to describe how the position, speed, and acceleration of this oscillating mass attached to the spring is related, okay? A mass is attached to a spring and it is oscillating, going back and forth like this, okay? Now, you start observing it when it is at equilibrium position, let's say. For convenience, you start observing when it is at equilibrium position. See, it's equilibrium position going back and forth like this, right? It's going like this, oscillating. But for sake of convenience, when you started tracking the motion, you starting from this equilibrium position. And then now you are looking at how it's going this way and coming back to the equilibrium position, and how it's going back, other side from the equilibrium position, and then coming back. So that's going to be one complete oscillation. So goes this way, comes here, passes, get past to the equilibrium, and comes back. So all this gonna give you one complete oscillation, one period of oscillation. So now, remember, when we started physics to describe motion, how did we do? We did the motion diagram, we made the graph, position versus time graph, we made velocity versus time graph, we looked at the acceleration, and then after that, we went to the energy concept. Do you guys remember that? We're gonna be doing exactly same thing for this oscillating object. So we're gonna be learning how the, position is changing with time, and then we're gonna plot that. And for convenience, I'm plotting x this way and time this way, okay? Just convenience. Usually what we did this, right? So what I'm doing here, since this thing is going back and forth, to mask the position this way, I'm drawing x this way. And then time is perpendicular to that, okay? That's all. So it's like rotating this by 90 degrees. Just that, right? So x arrives here and t goes there, down there, right? So that's what I'm doing here. So now let's keep track of the position. So this slide has a lot of information, lot of idea, concept behind oscillating object, motion of oscillating object, okay? So yes, of course, you are giving 100% all the time, but this slide is very important here, okay? So try to give 100+% here, okay? Okay, so now this object is here. So let's say that position is 0 position, x is 0, that's what I'm saying. So when it arrives here, that can be x is equal to, let's say, 1. When it arrives here, that can be x is equal to 2, and so on. So that means that's gonna go like that, isn't it? So those gonna be like that. If it was just the motion diagram would look something like that. But what happens? This thing is slowing down, right? Stops, and then it starts speeding up. So because of that, what happens? These dots, at first, since moving faster, the separation is going to be larger. And then what's going to happen? They're going to be crowded, slowing down, right? And then after here, stops, let's say. So that means that's the position. So that's how the position gonna look like if I'm tracking each those position every second, okay? But in the graph, what we do, we need to shift that dot with the time as well, right? So for the 0th second, it's here in 1st second. If it's there, so that means in the graph, it's gonna be there, right? So 2 coordinates, that's how we make the graph, right? So that's what I'm doing here. So what happens, since it's doing like that, so when it's there, that means the dot gonna be, so position gonna be there and time gonna be there. And remember, time, we always take equal interval of time. That could be 1 second or 1/10 of a second. Okay, so it's there. So it's a graph. So that's why that dot is there, not there. Okay, it's a graph, position versus time graph. If it were just position, it was just motion diagram, then this dot would have been, let's say, here. Okay. Now, since it's slowing down, what happens? It travels less distance the next second. Same time interval, but it's traveling a bit less. So that means it's slowing down, means slope. What happens? Slope decreases, right? Speed is the slope of position versus time graph. So it's the graph gonna be sloping less. So that's the maximum. Let's say that's where it stops. So when it's there, let's say position is there, right? So that's how far it reaches. That's the maximum position. And in this time, so that's how long it took. So the graph, the point is there. Okay. So now, see what's happening here. If I were to draw a tangent line between these, that's how it's going to look like. And between these, see, as you can see, the slope is becoming less and less slope, or let's say, yeah, slope is decreasing, right? And now, what happens? It's going to start going back. It's going to follow its footprint back. So that means these dots gonna just follow that as well. Since time keeps on increasing, they're gonna be just shifted, but they're gonna be at the same level. So here, if I were to draw a tangent, what's gonna happen? I'm gonna get straight line, means the speed is 0, okay? So yes, so now it's turning down, returning back, and arrives at this position. So when it's at that position, if you look at the slope, what's happening? See, it's moving backward, so that's why slope is negative. But near here, B is maximum. It's moving past it there because here it stops. And the other side do the same thing, right? It does the same thing. So that means moving slowly, and here fastest. Okay, fastest here, and then slows down, stops, and then it starts coming, you know, back, moving faster and faster. It becomes fastest here, and once it crosses the other side, what happens? It slows down because spring starts compressing. Okay, so spring pushes it in the different direction, opposite direction. So that's why it slows down. So now, once it arrives back, it starts moving in, let's say, negative x direction. Okay, so that means this dot gonna go somewhere there. But time keeps on increasing, so it's gonna just follow the path like that. Now, this is the position versus time graph. Okay, so if we were to connect this, yes, my drawing is not perfect here, but if I were to draw this, this is how it's going to look like. So that's how the position versus time graph looks like. Do you guys recognize that curve? This oscillating curve? If we were to use an equation to describe it, what equation would you write? Position and time, let's say. Do you recognize this is a sine function? Right? So that's why we can write this as a sine function. Here, A is amplitude, that's the maximum value. It arrives here, that's the maximum value. That's what the amplitude is, okay? And omega is angular frequency, and T is time. So omega times T, remember, omega is also delta theta over delta t. That's what we learned. So delta theta can be written as omega times delta t. So that's what that is. So you can think of this as an angle, okay? Think that as an angle. So if that's the angle, what happens here? When it goes from here to here, it has gone through the quarter cycle. So quarter cycle is like saying half cycle is like a 180 degree. Quarter cycle means like a 90 degree, okay? So quarter cycle here means period. In terms of period, it is T over, do I know how to write 4 like that? Looks like I don't. Okay, so that's the quarter period, okay? This is half period. And this is 3/4. And when it arrives back here, that's going to be a full period oscillation. So that's how we write the position versus time graph for oscillating object. Now, this is sine because we started observing from here. If we had started observing from here, that would have been something like this. That would be cosine. So it can be written either as a sine or cosine, okay? Or in between. That's also possible. So don't get surprised when you see, okay, x is written as cosine. It only means, it means just we started observing when it was at maximum position rather than being at equilibrium position, okay? That's all that means, okay? So omega is related to period, right? 2 pi over t, remember 2 pi f, omega is that, and f is 1 over period, means we can write like that. So we can write like this. So that's the relationship between position and time. And by the way, this t simply means position is changing with time. It's not position times time here, okay? So this is just a function of time. That's all it means. It depends on time. Now, how about speed? So speed is the slope of this. Here at the beginning, it is maximum. Over here, it is 0. So it's acting like if I were to plot speed at the beginning, it was maximum, right? And then by the quarter cycle, it becomes 0. So that's how the speed graph looks like. So it's a cosine, okay? So now this was the amplitude, maximum displacement. What is this then? It must be maximum speed. So omega A is the maximum speed, and we denote that by Vm, okay? And remember, maximum speed occurs when object is at equilibrium point. And similarly, we can also find the acceleration. And what happens is here, acceleration is maximum when the speed is changing maximum, okay? So here, near here, speed at the maximum position or at, like this maximum displacement position, what happens? Speed goes from this side to going to that side. So change is going to be larger at those points. And here the speed barely change, okay? So what happens is where position is 0, acceleration going to be 0 as well. And that you can easily see if you recall force is mass times acceleration. So that means it's going to be k times x. So when x is 0, a going to be 0. Okay. So what happens is position and acceleration, they are directly related. The only difference is one has a negative sign with respect to another one. So that means if I were to draw acceleration, I have to go this way. So that's going to be the acceleration. So when x is going positive, acceleration is negative. What does it mean? So for example, so this is attached to the spring, right? And it is moving this way, means acceleration is pulling towards the equilibrium position. So that means acceleration is this way. When it's moving this way, acceleration is that way, opposite, okay? Slowing down means acceleration is in opposite direction. So it's the sign again, but it has a negative sign. It's in opposite side, okay? So that's what the acceleration of oscillating object look like. And the equation is this, and this is gonna be the maximum value of acceleration, okay? AM. AM is just that, omega squared times A. So since A times sine omega t is same as x, we can write that as a x. So that's the very famous equation. This is very famous equation of oscillation that relates position and the acceleration, okay? So this is very famous equation. Another famous equation, PM is omega times A. And you find that in equation sheet as well. Similarly, A max is omega squared times A. That's another famous equation, okay? And when position has a sine thingy, then speed gonna have cosine. If the position was cosine, then B would be sine. They kind of opposite, okay? So that's how they works out. So that's what I'm saying here. If we had started from the maximum position, then the position would be cosine rather than sine, and so on. So yes, max or M means maximum here, okay, folks? So this kind of motion is called simple harmonic motion. So in simple harmonic motion, what's happening? It's repeating back and forth, and the acceleration and x, they are directly proportional. They are directly proportional, but their sign is opposite, okay? When that's the case, what happens? It becomes simple harmonic motion. That's the definition of simple harmonic motion. So see how we can translate that and describe motion of a wing. So this bird kind of flaps wing so many times every second, okay? It's going really fast. So it's going back and forth. So you can model that as a, let's say, simple harmonic motion, for example. So if we were to do that, okay, it says, go ahead, assume this is a simple harmonic motion. So by saying that, what's telling us is that we can use the equation we derived for simple harmonic motion to describe this motion, okay? That's what it is saying. It's not saying it's perfectly simple harmonic motion. It's not saying that, but it's saying, let's assume that, okay? Let's assume it's a simple harmonic motion. If that was the case, how would you use that equation to find this property of this motion, okay? So that's that thing, okay? So maximum displacement, which is amplitude, okay? So it may not say maximum displacement amplitude. It may either say amplitude or maximum displacement. Most of the time, that's what it says. And we denote that by uppercase A. Our book uses uppercase X. That makes sense because position and maximum. But A for amplitude is more standard notation. So that's why I like to use that, okay? So this is given in terms of meter over second square. So let's convert this into meter as well. To convert centimeter into meter, we need to divide by 100. So it looks like, yeah, that's how many meters it's going to be, right? And it says acceleration. See, acceleration versus maximum acceleration, they are different things. Acceleration keeps changing with time. Maximum is fixed for that motion. And we have a formula for that. And we assume so that means what is oscillation frequency? So there are two kinds of frequencies, omega and F. What is this question asking? When it says frequency, that means it's asking this. For this, it would say angular frequency, okay? So when it simply says frequency, just this frequency we are talking about, okay? So amplitude and maximum acceleration, do we know the relationship between them? We learned that A max is omega squared times A. We learned that in last slide, okay? So that's that. So since A given, this A given, and we know this F is inside here. So that's why this equation is suitable to solve this problem, okay? So let me rearrange this equation a little bit by moving things around. That way I can write like this. So now we are looking for F. So it is inside this parenthesis, or it's being squared. So to get F, we need to take a square root on both sides, right? So 2 pi F is A max over A under the square root. So F is going to be 1 over 2 pi make sure to differentiate your acceleration and amplitude. See, one is uppercase, another one is lowercase. We sometimes tend to just ignore upper or lower, right? But here it has a different meaning. So make sure you pay attention and differentiate them, okay? So now with this, now we should be able to find the answer, okay? So A max is 12 and this uppercase A amplitude is 0.0. So 12 over 0.05. So the unit of frequency is 1 over second, and 1 over second is also known as hertz, okay? So that's how we can model oscillating things in simple harmonic motion and use those equations we wrote in last slide, which I said was very important slide, okay? So if you understood that slide, that means you learned the kinematics of the oscillatory motion. Okay, let's move on. And there is this question. So recall the simple harmonic motion. What was the definition of simple harmonic motion? How force and position were changing, how force and acceleration were changing, okay? Okay, somebody did not get 2.5 on the last slide. Maybe I made mistake, or maybe you made mistake. Centimeters to meter, 100, right? So 0.05 sounds to be correct. So looks like you got more than that, way more than that. I don't know. So let's see what others got. Did you guys do the math and got number? Maybe I made mistake then. Yep, most likely I made mistake. Oh, somebody got 2.5 then. So somebody is getting 24. So that's like a 25 and 2.5. So 10th. We are off by 10th. So are you guys taking the square root first all the way down here? So I'll let you work one more time or two more time and, you know, see if you are getting same answer all the time, okay? Yeah, this 2 pi is dividing everything, okay? Okay, so now I'm moving to this question here. Hey, yes and no. Let's see what do we get. And you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Hey, where are we? Is there a way to delete this here? No. Is there a way to delete it here? Hey, there he is. Okay. So we got mostly yes, but some no. So let's say, like most of you, I'm thinking A as the correct answer. Am I right or wrong, and why? Did I see hand somewhere?
Hi, yeah.
Okay.
So I think that this is an example of simple harmonic motion because the perfectly elastic force is our restoring force in this example, right? And so from wherever I drop it becomes the V max, right? And then the restoring force is going to perfectly just cancel out that gravity, right? And so it's just going to keep bouncing like that forever. And so if I examine that over time, I would end up with this motion graph.
Okay, so here you are dropping from here, so your V is equal to 0 position is that, isn't it?
No, that's my max. Because the elastic force is going to keep restoring it all the way up. So it's going to end up bouncing somewhere between those two.
So if this is max, that would be max too, right?
Yeah.
So why would this turn around? It would just keep flying, isn't it?
I don't know. I mean, I
Something
mean,
to think about, isn't it?
Yeah. I would think that they would cancel out and it would just bounce in that same position forever.
Think about something like this. You are you are dropping a ball. And what happens? It hits the floor and bounces back up, right? And goes down. That's
Okay.
the that's what's happening here. So you are just dropping a ball, let's say.
Mm-hmm.
And Bmax is here right before it hits, right? And then it turns around,
Oh, okay. I
right?
see now. I see now. Yeah. All
Yeah,
right.
I think that may have caused some confusion there. So it starts with the Bmax here, okay? And then what happens? It's going up means it's slowing down, right? Because force of gravity is pulling down. Nothing is pushing it up, is it? That bounce thingy, elastic bounce, it's just giving you the same speed it came with. That's what happened. That's all the elastic bounce is doing, right? So now, for the simple harmonic motion, I think we can also write SHM for that. What has to happen? Force, or let's say position and acceleration, they are always in opposite direction. And proportional. What it means is when position is maximum, acceleration has to be maximum. And they have to be in opposite direction. So if it's difficult to see the acceleration, we can think in terms of force, because force and acceleration, they are proportional, right? And the only difference is mass. So one number gonna be larger than the other number, but the nature gonna be kind of same. So force, or another way to look at it, is something like this. It happens in a case like this. Force is negative k times x. Remember, that's the spring force, right? So x and f, they have to be always in opposite direction. But here, what's happening when it's, let's say, I don't know where you want to measure the position from. So for example, let's say if I start from here, when it's going down, force is also acting down. Gravitational force is acting down, isn't it? X and F, they are acting in both directions. But condition for simple harmonic motion is they have to be in opposite direction. So it looks like this is not a simple harmonic motion. So all oscillating motions are not simple harmonic motion. Let's keep that in mind. So to remind that, I brought this question, and many of you end up making mistake here. So I'm giving credit for all for now, okay, for this question. But let's keep in mind, all bouncing motions are, or oscillating motions are not simple harmonic motion. So it has to satisfy certain condition. And those conditions you can look in terms of position and acceleration, or force and position, okay? So now this is position versus time graph. We drew it, we spent some time talking about it. So now, how do you figure out velocity and acceleration, especially sign, based on that? So for this, I'm giving you maybe 1.5 minutes. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, we are looking for velocity, and this is position versus time graph. So how do we get velocity from the position versus time graph? From the slope,
Yep.
right? Yep. So to find slope, I need a dot next to that, and then draw a tangent line. So is slope positive or negative in this case? Assuming this side up is positive here.
Positive.
That's a positive. So velocity is positive. And how about acceleration? How do we find acceleration? Sign of acceleration.
The slope of the slope.
Slope of the slope. So for that, we need to draw another one here, right? So this is V1, this is V2. Slope is decreasing, is slowing down. Slowing down means acceleration is in opposite direction to the motion. So that's one way to look at it. Another one is this. I find this one easier always for simple harmonic. This is simple harmonic motion, right? So X and A, they have opposite sign. X is positive, means A gonna be negative. That's another way to look at it, okay? So B2 smaller, slope is smaller than V1. So change is gonna be negative. And acceleration comes from change in velocity. So that's one way to look at it. Another way, just look at the formula, okay? Okay, let's see how did we all do here. Hey, you guys are smarter than I am. It took longer for me to explain that. Okay. Now let's take a look at this one here. And you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see how did we do. We got more varieties here. So acceleration and force, they are directly related, right? So wherever force is maximum, acceleration going to be maximum as well. So where is force maximum? Wherever it is at the maximum stretched position, isn't it? Maximum stretched position going to be R based on this. Okay. So it looks like C going to be the correct answer in this case. Okay. Okay, so at equilibrium position, velocity is maximum. At turning position, acceleration is maximum. That's how it works, okay? A max here, B max here. And you can also tell that by looking at this equation here. When x is maximum, a is maximum. Remember this negative sign, so x is better, a is better. So negative sign simply means direction. It does not mean larger or smaller value. So whenever x is largest, a gonna be the largest as well, okay? So that's another way to look at it. Okay, so it's a break time, so let's take a break and we come back after 5 minutes. So I am trying to look, like how the velocity is changing. So for that, I'll just choose the velocity here and see how the velocity is, the arrow is very long near the equilibrium and how it gets shorter and shorter. And then it just flips the direction from the maximum displacement point. So that's the velocity. Maybe I can attach the acceleration too. Let's see if I can actually put the small mass, so that way it's going to take longer. Oh, what happened? Oh, my bad. Oh, there is spring constant. I can change that by putting large mass, and spring constant is smaller, gonna take longer time. Yeah, down there we cannot see the downward motion, but upward one from the equilibrium, we can see it, right? So now let me attach acceleration and see how acceleration is doing. Excuse me. So acceleration is also changing, but the length of the acceleration vector is maximum where the mass is turning around, okay? Yeah, it's becoming hard to see with this very large mass. Maybe I need to use... Okay, so you can always come back here and play with this. And later we'll see the frequency of oscillation and how that depends on the K as well. So you can change the value of K, make it smaller or larger, and you can see how that changes, right? So this is for spring 2. So if I were to make very large, then what happens? Hey, it's oscillating faster, okay? Okay, so for now, let's put this down here and let's go where we actually derive another important equation. Did I pull through this one here? Yep. So mass spring system, let's again write down the equation. We know the force on the mass is F is equal to negative K times X, right? So this, when this is moving this way, oh, so when this is moving this way, as indicated by arrow, the F is in opposite direction. They are in opposite direction, right? And What happens here? When x is negative, force becomes positive. So they are in opposite, they have opposite sign, I should say, okay? So force, it's given by just Hooke's law. And if I were to write mass, force in terms of mass and acceleration using Newton's second law, what I can do is I can solve for acceleration. And why do I want to do that? Because we learned that for general simple harmonic motion, or for any simple harmonic motion, we can write acceleration like this. Remember that busy page we went through? That's where we wrote it. So if I were to compare this, the acceleration, x, x, negative, negative, that means omega square is k over m. Okay, omega square is k over m. By comparing this equation, we can tell. So now from here, we can find the frequency. So omega is that. And if we were to write period, we can do that. Omega is 2 pi over t. Or if you want frequency, you can replace this omega by that and solve for f, okay? So that's the period of oscillation of a mass attached to a spring. And it says the period depends on two things. One is mass of the object attached. Another one is spring constant. Okay. So if you go back in that simulation page and then attach different mass for the same spring constant and look at how fast it is going, versus what you do is keep the mass constant and see how the K is changing the period. So larger K means period gonna be smaller. See how one is in numerator, another one is in denominator. So they have kind of inverse relationship, but not exactly inverse, but square root is there, right? So for example, if K goes to 4 times K, then T goes to 2 times T, just 2 times T when K goes 4 times. Oh, what happened here? So when K is that, T becomes not 2 times T, but half T, okay? With increased K, T decreases, okay? So it becomes half. But on the other hand, when mass goes, let's say 4 times M, then T goes 2 times T, okay? That's what this is telling you. And if you go to simulation phase, you can see that on the same simulation phase I showed you, okay? So now here is question for you. And you have 1 minute and 30 seconds to answer this question. Oops, oops, oops. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Mostly C, but we have A and B as well. So what's happening here? It says mass, certain amplitude and period. If the mass is doubled, the spring constant of the spring is double, M becomes 2M, K becomes 2 times K, and the amplitude is also double. A becomes 2 times A. This equation doesn't have amplitude in it, so we don't need to worry about it. It does not depend on amplitude, okay? So what does it mean is if you pull all the way down and let it go versus just pull a little bit and let it go, the period gonna be same. That's what it is saying. And of course, in simulation phase, you can go and try that, okay? So now, how about mass and K? So M, when it becomes 2, and K also becomes 2, means this 2 cancels, leaving it just M over K. So it looks like it's gonna stay same, just like most of you identified, okay? So now, when you are at, this space station, what happens? You are weightless because you are constantly falling with the acceleration g. You are in free fall along with the space station. So that means you feel weightless. So weight 0 does not mean you have 0 mass. So if you want to find mass, how do you do it? Your scale not going to give you weight. Here on the earth, we find weight. Okay, rather than mass, we find weight. And how does it work? We step into the scale. So that means we are pushing scale down and scale is reacting back with the normal force equal to our weight. So normal force is equal to mg. So when g is 0, normal force is going to be 0. So that means we're going to feel weightless. Okay. So yes, mg is 0, but m is not 0. So if you need to find how you are keeping up with your mass, if you put more mass, that means you are increasing the weight, right? And so to find that, what you can do is, rather than using that kind of scale, you can make oscillating scale. So attach a chair with a spring and set that in oscillation. So it's going to oscillate back and forth. So while doing that, what you do is you find the period of oscillation, how long it takes to go one complete oscillation, right? So T is 0.85 seconds, it says. And the spring constant is 2600 Newton over meter. So what is the mass? So period and mass and spring constant, they are related. I always kind of tend to forget, is this 2 pi on the numerator or in denominator, folks? Can you verify that? We need that in right place to get correct answer in this case. So we want mass, and it is inside the square root. So to get rid of the square root, what we need to do? We need to square both sides. So this becomes t square. Other side becomes 4 pi square. And square of square root is simply nothing. So it becomes like this. So now we can solve for mass. So 4 pi is in numerator, if I did write that formula correctly. uh, so that means m, to find m, we need to move this 4 pi square on this side and k also on this side. So what happens then? It becomes t square over 4 pi. Did I write that formula correctly? Did anybody check that? I'm kind of having a bit odd feeling here. So I got my k here, okay? I moved k. So that means now it's just a matter of plugging the numbers and getting the mass. And looks like we are getting 49 kilogram. See, you can keep track of your mass using that technique there. Now let's talk about pendulum. So there is tension acting and there is mg acting. So somebody is talking about unit here. So unit should be in kilogram. So how do we get that? So here time has a unit second square and K has a unit Newton over meter. 4 pi doesn't have any unit, so we don't need to worry about it. So Newton, what is Newton? We need to recall the definition of Newton. Newton is unit of force, and force is mass times acceleration. So that means it is kilogram, and acceleration is meter over second square. So let me write like that. And this mass down here, sorry, not mass, but the meter down there. So this cancels, has a negative 2 power, has a positive 2 power, cancels, giving us just kilogram. Okay. Okay, so back to the pendulum. So now, remember the net force is the restoring force. And it's easier if we write, let's say, we can assume a two coordinate system, one along this direction, another perpendicular to it, okay? And when we do that, t gonna be along the one of the coordinate system, but mg neither gonna be along this line or that line, so we need component of mg. So let's find component of mg here, okay? So since this angle is theta, this angle gonna be also same as theta. See, this angle is the angle made by this line with the vertical. So it's the same thing here, right? So now this component gonna be mg cosine theta, and this one gonna be mg sine theta. So this is adjacent for this triangle there, and this is same as that, but since we draw them from the object, we are moving that one there. So that's opposite mg sine theta, and this is adjacent cosine. It has a cosine. Oh, did I not write cosine anywhere here? So what happens? This mg cosine theta balances the tension. So the net force is just mg sine theta. Okay, so that force is the restoring force. Okay, that's what making this pendulum go back and forth. Okay, it's acting towards the equilibrium position. So this is the equilibrium position. Okay, so what we want to do is we want to find the period of the oscillation of this pendulum here, okay? And by the way, this T is not period, this is tension. And that T is equal to mg cosine theta. They are balancing each other in this case, okay? But here, they are balancing, they are canceling. Only mg sine theta is in action, okay? So that's the restoring force here. So restoring force, just like a swing force, it is kind of negative, okay? It's making it come back here, okay? X and force, they are in opposite direction. So when this thing is moving this way, the force is acting this way, okay? So that's what that negative sign means. Now, sine theta. So there is this theta. There is this theta. So sine of theta, and if this angle is small, this line gonna look like a straight line, right? And this is gonna be x. So in that case, sine theta gonna be x over L, opposite over hypotenuse, right? So we can replace that by x over L as long as theta is small, okay? So that means you do not wanna go more than 20 degree. When you convert 20 degree into radians, it's a small number, okay? So 10, 15 is good. So why I want to see like this? Because I know the relationship between force and X. I can use that just like a spring, mass spring system, okay? So that's why I'm doing that, okay? So now, hey, this is acting like a mass spring system, which has a spring constant of mg over L. So you can now use the same period, because this is also simple harmonic motion, because X and F, they are proportional, and they have opposite sign. So that's a simple harmonic motion. So now what I need to do is I need to replace that K by mg over L. So mg over L, so m gonna cancel, L gonna hop up there, okay? Fraction of fraction. So that's gonna give, oh, there. Now the m and m cancels and giving you this. So that's the period of oscillation of pendulum, okay? And you can actually, if you can make pendulum out of anything in your home, even the shoe, just pull some shoelace out from a shoe and then let it oscillate. That's going to be pendulum. Hey, I can make pendulum out of this. I can make pendulum out of this. So what it is saying is, although the period for the mass spring system, it depended on mass, but for the pendulum, it does not depend on mass. Whether you put larger mass or smaller mass, what happens? Period is same, but it depends on length. So for example, if I have a very short length, it goes quicker. I don't know if you can get some idea there. And if it has very long length, and of course you cannot see whole thingy, but see, it takes longer. That's what that means, okay? And there is simulation phase on that fate. You can go and take a look if you like, and you can see how it's oscillating. And there is pendulum in that simulation phase as well. So now, when we are walking, our leg is kind of acting like a pendulum, going back and forth, okay? So it may not be exact pendulum, but let's say we were to model that as a pendulum. What's gonna happen? we can use the equation we just derived, okay? So it says, I have a 1 meter long leg. Oops. So that means length. Oh, I have to be careful here. Leg. So let's suppose that's my hip, bit circular, okay? And then I have a leg like this. This looking like more like a person here, okay? But of course, I'm labeling this as a leg, okay? So now it says, this is 1 meter. Let me write this as a lowercase l. If I treat my leg as a simple pendulum with center of mass at the middle, center of mass is at the middle. So in a pendulum, length of a pendulum means from point of suspension to the center of the mass of this object. So when my leg is going back and forth, I cannot just use whole length of my leg as a length because center of mass is there. So length of the pendulum gonna be from hip to the center, okay? So that means length gonna be L over 2. Now it says how long it takes for me to walk each step. So let's say that time is what? To walk each step. So when we are walking one step, what is one step means in terms of period of pendulum? So our leg, one step means what? This leg goes from here to here. That's one step, isn't it? It goes from here to here. It's not like going from here to here and back, right? So time for one step is half of the period. Did I get that right? Do you want to try walking and see? See, one period means if you start from here, it has to come back to the same place. That's one period. But in one walk, I think we just, let's say if I'm there, one step means just going there, I think. Yeah, half of the period. So now I can use formula to find period. I don't know if I did half or not for the, so my number may or may not be correct, okay? You guys need to check, but the way I'm doing it must be, it is correct, okay? So if you have a long leg, your period is larger. And if you have shorter, of course, shorter. So that's why, I don't know if you have seen elephant walking. Elephant has long legs, right? And let's say there is elephant and dog is following elephant. What happens? The dog has to move its leg really faster. Period has to be shorter to catch with the elephant. Okay. Okay, so are we getting 0.7 second as an answer, or it's 1.4? Okay, sounds good. So there is another question right there. Let's make a clock out of pendulum. Have you guys seen big, the pendulum thingy, pendulum clock? Have you seen pendulum clock? In the old days, there used to be one with a large mass attached here, and then that went back and forth like that, and there is clock right there. Okay, so before these all electronic clocks were invented, that used to be the standard of time. Okay, and they put that inside the box so that the air resistance was minimum, and of course I'm guessing they had to open the box and give push once in a while. It's not going to last forever, right? So anyway, so here it says determine the length of a pendulum so that it swings back and forth in simple harmonic motion with a period of 1 second. So if you want to make a clock that has a period 1 second, right? One pendulum that has a period of 1 second, then how long the length you should be using? So that's the question, right? So T, I think I have done that here. I have written that equation. Since we want length, we need to square both sides to get the length out. So I can do that, and it is around 25 centimeter or quarter meter. Okay, so if you have something to measure and make pendulum, what you can do is, hey, I have a scale. I had a scale somewhere. Should we do a simple experiment here? A remote experiment? Let's see what happens. Okay, let me grab my scale. I have a scale, real scale here, folks. So what I'm gonna do is I'm gonna measure 25 centimeter. And remember, 25 centimeter has to be measured from the center. So yes, there's gonna be uncertainty there in length measurement, but I'll try my best, okay? And 25 centimeters. So from about the half, from the halfway, from about half of this bucket, I am measuring 25 centimeter. Do you see that 25 centimeter number there? Okay. So, do you have a stopwatch in your phone? So what you want to do is I'm going to set this in motion and you want to time for 10 seconds. So when I say go, you guys start your stopwatch in your phone, okay? And then when I count 10, you stop your stopwatch. Okay? Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. What's the time for 10 oscillation? 9.48 seconds. Hey, close to 10, isn't it? 10 divided by 10 is what? 1 second. And my measurements were, of course, there were large uncertainty there. You see that? See how nicely it works? We did all mathematical calculation and derived this, and it works out. That's the cool, yes, that's the cool thing about physics. You don't need to do experiment. You can just do theory, math, and can tell what's going to happen. And it happens. Okay? And it happens. Now you can make your own pendulum clock. So now here is a question for you. Do you have equation for period of pendulum? Okay. So this is talking about natural frequency. So whatever frequency it oscillates for a given length, that is its natural frequency. Okay. I mean period, and of course you know the relationship between frequency and period, right? So I'm giving you a minute to answer this question. Oh, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. Oh, oh, oh. Oh, oh, oh. What happened? So person sits versus stand up. What changed? Does G change? Oops, what happened here? G remains same, right? So length changes, doesn't it? Because center of mass shifts up. So length becomes shorter. So it stands up. Stands means L shortens. Center of mass shifts up towards the point of suspension, right? So there is swing, person is sitting there, right? And then what happens? Person stands up. So center of mass is there, means length is just this much. So L is smaller means T is smaller. T is smaller, but here the question is asking about frequency, not the T. And frequency and T, they are inversely related. T smaller means frequency gonna be greater. It's gonna go faster, okay? So it looks like A is correct answer in this case. Hey, it changes, it changes. One more question. And you have a minute to answer this. So this time is a period. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Mostly C, and that is correct answer. Why is that correct answer? Can somebody explain that? Period does not depend on mass. That's right, it's irrelevant for the period. That's right, Sila. Thank you. Okay, folks, I think we have one more question about the period of the pendulum. Maybe we can start from here next time. Or you guys can first try and maybe we'll do it here, okay? So for the pendulum simple harmonic motion, mass doesn't matter. But for the mass spring system, it does, okay? I saw that question on the chat, so that's why I'm talking about. Both are simple harmonic motion though. So in some cases it does, in other cases it does not, okay? So let's keep that in mind. For the spring, there is this. So there is mass in the equation, means yes, it matters. But for the, so that's for the spring. But for the pendulum, that means it doesn't matter. It does not depend on mass, okay? So we need to remember, equation is telling us things, we need to listen, right? Okay. Okay, folks, have a nice break and happy Thanksgiving. I'll see you guys week after. So assignment's gonna be due a week after, okay? The week we come back.
Thank you.
Have a good week off, everyone.
Thank you. Same here. Have a great Thanksgiving break.
Have a great Thanksgiving, guys.
Thank you. Have a great Thanksgiving.
I'll see you later, Dr. Ngana. Have a good day.
You too, Crow. Enjoy your week off.
Yeah, you too. I'm finished. It gives me all the time I needed to finish up my application, so
Yeah.
I'll be busy. But